Before we start, if you're enjoying these conversations, please make sure that you like or subscribe to Cleaning Up. It really helps other people to find us. Cleaning Up is brought to you by Capricorn Investment Group, the Liebreich Foundation, and the Gilardini Foundation. Hello, I'm Michael Liebreich, and this is Cleaning Up. Now, Cambridge University has a great tradition of producing brilliant energy analysts. And no, I'm not talking about myself. I'm talking about, for instance, the late Professor David Mackay, author of the classic Renewable Energy Without the Hot Air. And my guest today on Cleaning Up, it's Professor David Cebon. He is the director of the Center for Sustainable Freight. He's a researcher across the energy landscape and also a founder of the Hydrogen Science Coalition. Please join me in welcoming Professor David Cebon to Cleaning Up. David, thank you so much for joining us.
Thanks, Michael. I'm very flattered to be invited, particularly given the esteemed company that I'm joining on your show, and to be compared with David Mackay is certainly a great honor. Thank you.
Indeed. And it's always sad to remember his loss, because he was such a clear and loud and insightful voice in this space. We would be in a better place had he been able to continue the work that he was doing. But sadly, it comes to us to try to pick up and do what we can.
Absolutely. He was also a great communicator and really clearly illustrated the real nub of the issue, understanding the numbers and communicating the numbers and the big issues around land use and the challenges of getting to a renewable future. So I'm a great admirer of David's.
Now, I don't want to go down in the direction of critiquing David Mackay's work, but he also, I believe, he didn't quite get his head around the extraordinary advances. So the fact that we've got 15 megawatt wind turbines pushing at 20, the increases in efficiency in solar and so on. But that's not the issue here today. What I want to do, before we dive into some of the areas that you and I have interacted on, what I'd like you to do is give a bit of a thumbnail bio. What is it that you work on? You know, who are you? My audience is a generalist audience. Some will know you and some won't.
Well, yes, thanks, Michael. You possibly detect from my accent that I come from Australia. I came to the UK in the very early 1980s to do a PhD, and I kind of got stuck, and I'm still here. I've worked really my whole career on heavy goods vehicles, believe it or not. Is that a thing, that you can work on heavy goods vehicles as an academic? I worked for 15 years or more on road damage caused by heavy vehicles. Then I spent a lot of time looking at safety and things like braking and rollover and turning and maneuverability. And for the last 15 years or so, I've been working on sustainability and decarbonisation of heavy goods vehicles. And of course, as soon as you start to talk about decarbonising heavy goods vehicles, at least in the last 5 years, you come head on with hydrogen because heavy goods vehicles are one of the early uses being touted by the hydrogen industry. And so I've become very interested in hydrogen for heavy goods vehicles, and that's led me to investigate it for other applications as well.
It strikes me that one of the things I enjoy about reading your work is that you take a whole system approach. So you could be quite happy with, you'd probably have a perfectly happy academic career and possibly even be financially better rewarded if you said, well, let's just use hydrogen for heavy goods vehicles. It's the hydrogen will be there and we'll just use it and it'll be fine. It'll be a drop in. Many of the industry structures will remain unchanged. So, why have you found yourself having to look beyond the confines of the industry?
Well, that's a great question. I think that when you look at decarbonisation and the energy transition in general, it's essential to take that systems view, particularly when you're looking at carbon, because it's very easy to say, well, look, here's a really fabulously clean solution when we look at it through in this sort of window or this boundary. And then if you look at it in the wider sense, you discover that it's actually terrible. And that's definitely the case with hydrogen. If you look at hydrogen just from the point of view of an individual vehicle, it looks like a pretty good decarbonisation solution. But when you ask the question, where does the hydrogen come from, you get a different answer. And the carbon footprint of hydrogen manufacture and the implications of hydrogen manufacture are pretty severe and is what kills it from my point of view.
Let's take us that statement as a starting point, right? You've got a value chain there from hydrogen production through to the heavy goods vehicles and other things that you've looked at. But let's take the system thinking as a starting point. Could you describe, with the benefit of all the work that you've done, particularly over that work on the last 15 years on sustainability, what does the UK energy system look like in a net zero future? And I'm going to assume that most of what you've done is UK based, although you may want to use other examples. But where is that going?
Well, I think that's a great question. The first thing is that to decarbonize the UK's economy, we really need to electrify everything that can possibly be electrified. And that means, to me, certainly the key big, the big elephants are transportation, ground transportation, and heating. They need to be electrified. If you don't electrify those, you end up with really dramatically increased energy demand, and in a way which we can talk about, but which is really not achievable in my view. So you have to electrify. It needs to be clearly renewable. Offshore wind and onshore wind increasingly will be the big part of that. Some solar. There is the nuclear fleet still exists, and that's important to keep that running. I have my doubts as to whether the country will be able to build much more nuclear, because I think it's kind of politically very difficult, long-term. It's too expensive at this point compared to renewables. So I think for all those reasons, nuclear is not likely to increase, but we'll keep it going. So they would be the big components. The challenge with that mix is that with electricity, of getting supply and demand to match, and that's a problem on two scales for the UK. One is the daily demand cycles and availability of renewables. To meet those differences between supply and demand, I think we'll do a few different things. The first is that we'll overbuild some renewables, and to some extent, we will curtail, probably overbuild and curtail to some extent. That's economically a reasonable thing to do. Not a huge amount, but there'll be some of that. The second thing that I think we will do is increasing demand management. And, there's some great examples of that, like Octopus, where the electricity industry can manage demand, manage pricing to level out demand. And I think that's the second thing. And the third thing is that we will have to have some storage. And there will be a modest amount of storage to solve this particular problem of the day-to-day fluctuation of supply and demand. The amount of storage needed is not that high, and can be achieved using a combination of technologies, and we can talk about what those technologies might be. But at the end of all of that, you end up with a system which has got firmed power across a day or a couple of days. Maybe you have storage so that if you have a day or two when the renewables are down, are lower, you have a day or two storage. You then have the problem of summer to winter. And the winter usage, the winter consumption of electricity in the UK is currently about, on average, 8 gigawatts higher than summer consumption, something like that, over a period of about 200 days, which is essentially the winter period. So the UK uses more power in the winter than in summer. And the question is, how do you do that? How do you solve that problem? It's not the only problem, but it's one that you have to solve. One approach is to build salt caverns and fill them up with hydrogen. That's one approach that's being proposed. The amount of that required is pretty mind-boggling, because if you integrate that 8 gigawatts by 200 days, you end up with terawatts, 16 terawatts, or at the current consumption rate. And that's really large. And my calculation is that would take something like 160 of the largest salt caverns, 500,000 cubic meter salt caverns at running at 200 bar. It's a mind-boggling project to make enough storage to do the UK's winter, summer, seasonal storage. And actually, I don't think it's practical, because, of course, not only does the UK have to do it, but Germany has to do it, and the Netherlands and France and everybody else has to do the same thing. If we go for this idea that what we're going to do is simply store all the energy that we need in the whole world has got to be building salt caverns full of storage by 2050. I mean, and then frankly, that's not a thing that's going to happen. I think it's ridiculous. I think it's a ridiculous concept.
Okay, although, just to be clear, that is on the basis of essentially sizing the system for the summer and then preparing for the winter. So now you're going to tell us what we should do instead.
I am going to tell you what we should do instead. So the other thing, of course, there's a number of other assumptions in what I've said. The first and most important is that it doesn't account for the fact that our electricity demand is going to increase dramatically, and we will need a lot more electricity in the summer to power all those heat pumps. So my number is probably out by a factor of 2 or 3 in terms of storage that you would need. My opinion here is that the answer is to import the energy using high voltage DC interconnects. If you do that at the current electricity consumption rate, that 8 or 10 gigawatts is perfectly doable. You know, there's a HVDC connection in China, which runs at 12 gigawatts, and it's 3,000 kilometers long. So 12 gigawatts and 3,000 kilometers would get you from North Africa to the UK, and they've got all that excellent firm wind and solar power in North Africa.
David, just to be clear, we had an episode on X-Links, which is 3.6 gigawatts, doing exactly that. We had Simon Morrish on the show. I can't remember which number the episode was. We can put it in the show notes. And I'm an investor, so this is music to my ears. David, Cebon says, I'm going to make lots of money because that's a great idea. But that's 3.6 gigawatts, which is about 8% of the UK's peak power now. Okay, power will grow. That might become 5% or 4%. But how many percent of UK power would you feel comfortable coming from North Africa in undersea cables, given particularly what we've seen with what happened to Nord Stream 2 just a few weeks ago?
You clearly have to diversify. You don't want to be dependent on one source. I think the amount needed, current amount needed, is about double that. So it's not a huge amount, and that just covers the winter-summer difference, right? So assuming we've got enough renewables and storage to manage day to day, we just need to increase the average, and that would require current consumption about double what X-Links is going to provide. I think the world needs to have diversified and interconnected electricity systems.
Can I ask why do you go with HVDC for that 8 gigawatts? Why don't you just oversize and say, well, you know what? We're just going to do overcapacity. We're going to curtail more during the summer. We're going to put, we're going to maybe store what we can. We're not going to do this ridiculous, 160 hydrogen in salt cavern storage, because that's simply unfeasible, as you quite correctly point out. Why don't you just oversize, and then, it's right sized for the winter and it's oversized for the summer, but we're not dependent on somebody else's cable from somewhere else, which everybody else, by the way, is going to be competing to do as well.
I think that is a perfectly reasonable thing to consider, and it's all about optimizing the economics, isn't it? If you have the economics and the energy security, the current situation, I've got to say, from an energy security point of view, this is a way better solution than what we've currently got. We're currently importing 50% of our gas, and it's coming from our friends in all kinds of places where we don't really want gas to be coming from. And
Norway and our own North
and
Sea.
Norway,
I mean, we mustn't go overboard on that one.
Sure, it's 60% imports. And so that's and it's dirty what's coming in, right?
But I'm going to throw a scenario at you, which you will have heard before, which is what the Germans called the Dunkelflaute, which I call the dark doldrums. And that is where there are some weeks of very low wind production. And when I say very low, I don't mean that there's 8 gigawatts that could drop out. We can see times lasting many days where wind output, even when you've built out and you've got the law of large numbers, you could be, I'm going to say, if we've electrified everything and our demand is now not 50 gigawatts, but it's now 80 gigawatts, what happens when you're missing 50 gigawatts of supply because of a weather situation that might last, 3-4 days, a week, maybe even longer?
Well, I think that's a very useful question to ask. And my personal opinion to that, personal response to that is that what you do is you keep your combined cycle gas turbines, your CCGT capability, in a form where you can spin it up if necessary. And the advantage of that, first of all, of course, we're approaching this future from the current situation where we've got all this kit operating and we're gradually using it less and less, right? So that's going to happen out into the foreseeable future. To 2050, we'll use it less and less. But we have the option, we can decommission it or we can keep it. Now, all of the sunk energy and sunk carbon cost and sunk capital cost is there, right? So you're just talking about maintaining these things, keeping them ticking over so that you can fire them up if necessary. My opinion is that that's a far better thing to do than spinning up a whole big hydrogen economy and, all those salt caverns and sort of ridiculous fantasy ideas that are being proposed for how to do this. Much better to keep the CCGT fleet if you need it for a couple of days a year or a couple of weeks a year. So, you spin it up. And frankly, Michael, if when I die, we've got to the point where we just use the CCGTs for a week or two in the year, and that's the sum total of our carbon emissions, I will die a very happy man.
Okay, but if I was I don't know, I'm not sure that my impersonation of an Extinction Rebellion or a Just Stop Oil protester is particularly good, but I would say, that is the typical sidestepping of the issue. We've got to stop burning stuff. You're saying we should keep this kit, and you all know what's going to happen next is whoever's got that kit is going to want to use it, and they won't be wanting to use it 2 days a year or a week a year. They will be trying to use it 30, 40, 50% of the time. We're going to go nowhere like that. How do you answer that?
Well, the first thing I would say is, in this regard, the perfect is the enemy of the good. If the perfect solution is to completely switch off all fossils as quick as we possibly can, and to fire up this hydrogen economy in order to make that work, it will make things much worse. And the Extinction Rebellion people, I think, can probably have that explained to see just how much worse the decarbonisation process will become if we've got to do it all with hydrogen rather than just by electricity. What we need to do is to decarbonise as quickly as we possibly can. The last few percent are important. They will become increasingly important, but the problem now is not that last few percent. People, the argument that we have to focus on hard to abate sectors is ridiculous. What about the easy to abate sectors? Let's get the easy to abate sectors done. And that means heating and transport to get electrified. So I think that's where we need to focus. It will be the case that the possibility of what you've suggested is that gas will be used more than it needs to be. That does exist, and we need to think about how to manage that, perhaps through some sort of regulation to prevent it from happening. But I think that the quickest way to get where we need to go is to electrify as fast as we can, and to not have the Dunkelflauter being the tail that's wagging the whole big dog, right? Let's deal with the Dunkelflauter by just keeping those CCGTs available if we need them, and do everything else by electricity as quickly as we can.
Very good. Now, and I have to concede that I also, if I could leave this world or leave this country at a point where, we've dealt with 95% of the problem and we've only got 5%, which is very intractable. But, I got really smart kids, there's lots of smart students that you teach, and, they need to have something to work on, right? Let's try and stay at the system level for a moment and talk about hydrogen. The UK currently uses, I believe it's 770,000 tons of hydrogen every year. And that is overwhelmingly, and I mean 99% plus overwhelmingly, from fossil fuels. What is your vision? And that's used in, for those in the audience who are newer to this, that's in fertilizers, it's chemical feedstocks, and it's also in refineries for doing things like hydrocracking so that we get the right mix of diesel and petrol out of a barrel of oil. What is your vision for hydrogen in that, we accept your overall architecture? What is hydrogen going to be doing? And then we can get on to what it's not going to be doing.
Yes, well, it's certainly going to be doing fertilizer, isn't it? I mean, we've got to feed a population now of 8 billion people. And so fertilizer is number one on my list for hydrogen. And, if politicians want to do something right now, this minute, what I would say is make that grey hydrogen that's being used for fertilizer green, and do whatever you need to do, because there is no alternative to that. I'm going to jump in here, right? And I'm going to challenge you on that, because here's the problem with that: is you said make the grey fertilizer green, right? But that means you've got some renewable energy, right? And if you do, why wouldn't you put it in a heat pump or an electric car and you'd displace far more carbon by not doing the fertilizer first? All of those things need to be electrified. While there's controversy about heat pumps and transport, there can be no controversy about that green hydrogen for fertilizer. I mean, I think that the other aspect of fertilizer is, of course, much more efficient methods of agriculture, which don't involve spreading fertilizer around the place, and we should be clearly encouraging that sort of more efficient farming as well. But I feel that was a bit unfair, because I said let's talk about hydrogen, not the other things that it shouldn't be doing, and then I kind of shot in a chip shot from the side there. But you're right, and of course the other thing is that the green fertilizer could easily be imported from
a Morocco or a Chile or a Namibia or an Australia or whatever. And I personally believe we're going to do a lot of that. But I think that point that you made about fertilizer, perhaps, I know that if we just left this out there, you use the word, we've certainly got to continue using fertilizer with 8 billion people. And there are those out there that would say, no, we don't. We're going to do completely different types of agriculture. How quickly do you have a sense of how quickly we could do that?
I'm not an agriculture expert in any sense of the word, so I couldn't really comment.
That's great. We found a system boundary, but I can tell you
right.
It's going to be decades and decades. I think you'd agree with that.
I think the transfer to green fertilizer is, that's a doable thing. It is a massive job. I mean, just decarbonizing existing hydrogen uses is a massive job. As you say, that 700 million tons in the UK. Did I get it right?
770,000.
Because
there's 94 million globally,
right.
but we're relatively small compared to places like China and Brazil and the US and so on. So we're just under 1 million tons.
Across the world, that is a massive issue, and one of the first ones that needs to be tackled. I mean, the other uses, a lot of those petrochemical uses will go away as we stop using fossil fuels for transport and so on. There will be a residual chemical use for polymers, which is something like 10 or 15% of that. And then there will be, and the other industrial uses for glass making, possibly for steel. And I think steel is the interesting one for me because it's such a big number. It's like 7 or 8% of world emissions, carbon emissions. It's such a huge amount. And I think of that, I mean, it's the same scale as trucking industry, which I'm interested in. It is a huge amount. And one of the possibilities for steel reduction is hydrogen. It's not the only one, but it seems to be a front runner at the moment. And that would require a massive, massive amount of hydrogen.
And of course, for the listeners, I think by now probably familiar with my hydrogen ladder, which I've talked about on a number of episodes and presented in all sorts of fora. And those uses that you started with, fertilizer, hydrocracking, methanol, chemical feedstocks, that's the 94 million tons that's already being used. We've got to green it. It's row A. Row B has steel on it. It also has shipping, because that seems to be one of those very difficult areas. It's very unclear how we're going to decarbonize the fuel used in ships without somehow going through hydrogen. Do you agree with that, or have you found some other cunning pathway?
I'm a sailor myself. I think that's a good solution. Shipping is probably the most difficult to abate sector, I think, in the end. And it's relatively small. It's a couple of % of carbon emissions. And so it is not the one where I would start. And I think that's important. It's important we start with the easy to abate sectors. Now, where you end up with shipping, I have my opinions, and I certainly know if I was the king of the world, I would say that all biofuels should go into shipping. Now, that's not a straightforward thing to do.
Not aviation.
No. Well, my reasoning for that is, so for a start, I don't believe in hydrogen for aviation. I believe in drop-in replacement fuels. And so sustainable aviation fuel or biofuel are the two possibilities. If I was the king of the world, I would say I would reserve the biofuels for shipping, which is much, much more cost constrained. So shipping, they use bunker fuel. It's the lowest of the low. It's the stuff that comes out of the cracking column just before the bitumen that we make roads from. And it's really, really cheap. To go to something which costs 10 times more for shipping is very difficult, which would be a synthetic fuel. So biofuels are much more in the realms of feasible economics for shipping. On the other hand, aviation, I think, is less price sensitive. People can, it's largely rich people being transported around the place, and it has much more price flexibility, price elasticity. So I would say that if you've got a choice of where you use a biofuel, it would be better off in shipping. The problem, of course, if you do that, somebody once said to me, look, once the biofuel is available, aviation will gobble it up. Aviation will be able to pay more for it, and that will leave shipping we don't know where. So that's why you need to be king of the world, because
the aviation in your world, as King David, as King David of the world, aviation would then be using a very expensive, but presumably that would be an e-fuel. So hydrogen and direct air capture, or something that's non-biological, because if it was bio, you'd put it into shipping.
Yeah, I think so. Well, I mean, possibly you have some biological feedstocks for your.
Okay, and now, so I'm glad we found one use case beyond the replacement, which is then the aviation, the sustainable aviation fuel based on an e-fuel. And, maybe if we sort of tried harder, we might find one or two niches. But I want to move on to that hydrogen. Is it all green, or is there any space at all for blue or any of the other rainbow of colors that we told pink and red and turquoise and whatever that we're supposed to get excited about?
Well, that's a very good question. I think the most important one is yellow, which nobody talks about. What is yellow hydrogen?
Yellow is from solar, right?
No. Well, I don't know. In my rainbow.
Yellow is just from electricity.
From electricity, from grid electricity.
See, I was a good student when I was at Cambridge. I almost was in the right year to study under, but not quite. A bit too old for that.
I don't think we had that rainbow back then. No. But
okay, so it's electrical hydrogen is what you want to see.
Well, so I mean, it's nice to talk about green, but then you're talking about dedicated new renewable assets. We do need lots of dedicated renewable assets, but in the end, when you build those, it's at an opportunity. If you use it for making hydrogen, you're not making something else. So the opportunity cost is decarbonising the rest of the electricity grid, and I think that's so. I'm a believer in actually when we use electricity using grid average carbon, and that means that rather than the marginal additional wind turbine. So it's important to consider the average carbon intensity of the grid when you're thinking about the future. And that's where.
Let me just make sure I've understood, and that might, for the audience. Yeah. So what you're saying is, if we insist it has to be green, then we'll build some wind farms and some solar to make green hydrogen, but then we might not use, that might displace some renewables elsewhere in the system. So actually it's not as clean as it kind of looks. Is that a fair statement?
I think that's absolutely right. And at the scale that people are talking about for hydrogen, it's a really massive amount of green electricity needed, which you can't build that massive amount of electricity and also do all the other stuff that we've been talking about decarbonising.
Because the assumption behind what you're saying is that you can't just build more renewables. Because I have this discussion quite a bit with on Twitter and elsewhere, where I'm very clear that the supply chain for renewables is constrained. The supply chain, the rare earth minerals, the land use, which of course Professor Mackay always talked about, the planning process, all of these things are constrained, and therefore you just don't have infinite renewable electricity to do this and this and this. And in fact, the A and the B rows of my ladder, the top two, between them would use more than 5 times all the wind and solar ever built to date if we were trying to do that.
Well, that's a great calculation. I think that's absolutely right. And I agree with you entirely. The little calculation that I've done on this is just around, I've done a few, but one is around heating, right? So if you wanted green hydrogen for heating in the UK, you would need an installed wind turbine capacity, offshore wind capacity of 385 gigawatts. Now, that's about 10 times the current average electricity demand of the country. That's just to heat homes using green hydrogen boilers. So because of all of the losses in that chain. So the idea that you're going to decarbonize the grid while also building out 40 times more renewables than we currently have. Well, we currently have 11 gigawatts of offshore wind. We're talking about 385 gigawatts of offshore wind to heat the UK's homes.
You've got this great graphic which compares, I don't know how I think you came to 270 gigawatts or something like that on the graphic. I'm not sure. It's not, was it, or is it 385? But anyway, but it contrasts it with the amount that you would need to build in order to heat the same number of homes using heat pumps. Can you give us the numbers on that?
Yeah, well, so the calculation is that on average in the winter, the UK uses 70 gigawatts of heat. UK homes take 70 gigawatts of heat. Now, to generate that 70 gigawatts of heat, if you go via a hydrogen route, you've got a green hydrogen route. You start off with a large amount of wind, offshore wind or renewables. You electrolyze at about 75% efficiency, and then you have to compress it and transport it and so on, and finally burn it in your hydrogen boiler, condensing boiler, and the total losses through that are about 50%. So that means that you need, if you want 70 gigawatts, you need about 150 gigawatts of renewable electricity. And to get that renewable electricity at the grid factor of the North Sea, my calculation is about 385 gigawatts of installed capacity. So that 385 gigawatts give you 70 gigawatts of actual heat. Now, the heat pump, on the other hand, is a miracle of wonder, modern engineering. To get that 70 gigawatts of heat, 2/3 of it can come from the environment, from pumped out of the environment from a heat pump.
Possibly 3/4 because the technology continues to improve.
Exactly. So it depends on the so-called coefficient of performance of the heat pump, depends on the technology that you're using there and so on. The upshot of that, so you just need enough electricity to run those heat pumps. And where do I end up? I've forgotten what the numbers are. I think that the total installed capacity is about 60 gigawatts of offshore wind turbines. It's a sixth of what you need. So I need to get those numbers straight. I should have put the graphic on the screen.
What we'll do, David, is we'll put a link, in fact, into the, I mentioned the Hydrogen Science Coalition, which I'm not sure if I think I mentioned in my introduction. If not, it's an important thing that you've done, and we'll link to that, and we can link to the specifics with the numbers in the show notes.
Excellent.
But all of that. So you've got a ridiculous amount of offshore wind that you will have to build if you want to do green hydrogen for heating. Ridiculous, completely inconceivable. Okay, that's a fantastic reason to do blue hydrogen, isn't it?
Right. So blue hydrogen is interesting, Michael, and you and I have disagreed on this in various ways. But let me tell you my take on blue hydrogen. So the problem with blue hydrogen is that there are numerous problems. The first problem is, of course, that hydrogen is not as energy intense. It doesn't have the calorific value of the gas that you make it from. So you take methane, you reform it with hot steam, you take the carbon, and the carbon is the good stuff, right? I think people think that hydrogen is the good stuff in methane, but actually it's carbon, which is the good stuff. It has the highest energy to burn it. So you strip off the good stuff, you mix it with oxygen and turn it into CO2 and put it down a hole in the ground, and you're left with this much lower calorific value hydrogen. Now, what that means is that if you want to provide the same amount of energy through using hydrogen instead of methane, you have to start with a lot more methane. You have to start by importing 40 or 50% more methane in the first place. So the very first thing that happens is our energy security problem gets a whole lot worse, because now instead of importing 50% of all our gas, we have to import 60 or 65% of all our gas. That's it. So energy security is an issue, and the cost, of course, there's the cost of importing all that energy. The other problem is with blue hydrogen is that it's not necessarily as clean as we might hope. And this is where we don't necessarily agree, but let me tell you the three issues. The first issue is the fugitive methane emissions, the upstream methane emissions. In really, really good gas fields, and some of the really, really good gas can have 0.1% fugitive emissions. This is emissions through flaring, venting, and leakage. And I don't know if you've seen the fabulous BBC documentary about big oil versus the world. Big oil versus the world, but there's some amazing footage of the methane leakage in US fracking industry, and just showing the amount of methane that's going up into the atmosphere. So the worst places in the world, that can be 3% or more. So that's the first problem, is that some of the gas coming in is very dirty.
And to point out to the audience, it's an incredibly powerful greenhouse gas. So when you get to 3 or 4% loss, you might as well not bother. You might as well just use coal or whatever, right. You're done.
Right. So that's my second number. So we've got one number, which is the percentage of fugitive emissions. 0.1% for really great, 3% for really, and 1.5% average in the world or something like that. Number two is, how bad do you think methane leakage is? And there's different opinions. Some people say we should consider methane on a 100-year basis, which means that it's 24 or 25 times worse than carbon dioxide. Some people say we should consider it on a 20-year basis, in which case it's 86 times worse than carbon dioxide. I don't understand the 100-year basis, because the stuff is only resident in the atmosphere for 12 years. So, and I think that we've got real problems now with all of this. We're not going to leave it for 100 years for our children to deal with. So my opinion is that we should be using the 20-year basis, which is back to 86. The third issue is the carbon capture and storage in the blue hydrogen manufacture. The current technology that's around is capturing about 50% of carbon emissions. It's thought that if you change from SMR, steam methane reforming, to ATR, autothermal reforming, that you can get that to be much better, maybe 90%. But they don't exist. Those plants don't exist in the world. So the debate around blue hydrogen, on the one hand, you can take the worst of those three numbers. You can take the existing level of methane emissions. You can take the global warming potential of 20-year global warming potential, and you can say, well, look, we're going to convert existing grey hydrogen plants to blue, and the best we'll do is 50, 60, 70%. Or you can say, well, the future is going to be, we'll only use certified methane from 0.1% leakage source. I don't see how we can get around the 86, but we will only use plants which capture a really high level, 90, 99%. Now, if you manage to do all that, you will have hydrogen which is fairly clean. If you don't, you won't. In fact, you'll have it being pretty dirty. Now, I think we agree on all of that. So where we don't agree is, what is reasonable to assume for the future? Do we assume kind of retrofitting business as usual technologies and the fact that there's all this methane leakage in the world, or do we assume that we can get to this fabulous, clean future world?
And maybe that is the nub of it, in that I don't assume anything. I think it's up to us to decide, us as society,
Yes.
us as, as thought leaders, academics, commentators, whatever I am, to say, look, if you want to do blue, if you want to do lots of hydrogen, you can't do it all green. We've talked about that. You have to do, if you really want to do a lot, and by the way, I think we have to do a lot because of shipping and aviation and the stuff at the top of the ladder. And therefore, we have to do it clean. And that means not 90% autothermal, but I actually think that the standard, and you and I have talked about what a clean hydrogen standard needs to look like, really ought to be probably 0.2% fugitive methane and 95% plus carbon capture. And if they can't do that, then I think that should all be just shut down and walked away from. So I think we'd agree on that.
So we would agree on that. BEIS, the Department of Business and Energy and whatever else they are, is not, they've got a standard, which is effectively 2.4 kilograms of carbon dioxide per kilogram of hydrogen. Now, just to put that into context, if you just make grey hydrogen, it generates about 10 kilograms of carbon dioxide per kilogram of hydrogen. If you go for the BEIS standard, 2.4, it's about 75% less. My calculations is if you use that BEIS blue hydrogen standard for heating, that within about 3 or 4 years, it will be dirty. Just with the current rate of decarbonisation of the electricity grid, it will, within a few years, that blue hydrogen standard will be obsolete and will actually, any plants that are built to that standard will be a carbon source, a problem carbon source.
And this is a classic example of regulatory capture where the industry says, well, it's better than what we do today, so it's a start, whereas it's actually a dead end. It is not compatible with a net zero future. It's going to leave you with too many emissions to buy offsets. David, I'm just conscious of the time because we did talk about trying to get you out at the top of the hour, and we have to talk about transport and trucks, which we've not started on. And, let's just do the following. Let's assume that everybody agrees that fuel cell cars are done. They're just not going to happen. There's still some people who say, yes, and BMW is doing a pilot and this and is going to make a few. And I think that let's just assume that we all agree that they're going to have horrible sales figures and stop doing that. And the same with Stellantis and the same with Toyota and whatever. But now trucks, there's a lot of people say, oh, but the truck, the heavy goods vehicle is the absolute natural use case for hydrogen. So what do you say to that?
I'll give you a very quick potted version. The first thing is the hydrogen truck costs twice as much as an battery electric truck. Why is that? They're both actually battery electric trucks. They both have electric drivetrain, a battery, an inverter. The difference between them is that the electric truck has a bigger battery, and the battery electric truck, and the hydrogen truck has a hydrogen fuel cell, hydrogen tanks, hydrogen delivery equipment, all expensive, actually rather heavy, and that really increases the cost. So just at current prices, you can go and buy a 44-ton track unit for 44-ton truck, cost you £300,000 in a battery electric version, £600,000 in a hydrogen fuel cell version.
Okay.
I know that.
But I'm going to say, experience curve.
Okay, well, that may be, but in the end, it's capital expensive, much more expensive. Capital is much more expensive technology than just adding the battery. And the experience curves on that additional battery are, of course, being brought down way faster because of the whole electric vehicle industry. So on capital cost, you're at about double. On energy cost, you're at about 3 times because of the inefficiencies of using hydrogen. So here we go. I've got an industrial partner. I've got lots of industrial partners in the logistics industry. I say to my industrial partner, okay, you can have this vehicle A, which costs you X to buy and Y to run. And you can have this vehicle B, which costs you 2x to buy and 3x to run. Which one are you going to buy? Well, it's quite clear. You buy the one which costs you half on capital and a third on running costs, as long as it will do the logistics that you need it to do. That is the question.
1 second. Why is the hydrogen 3 times as expensive? You put that out there, and I'm going to have, the comments are going to be full of people saying, no, it's all going to become cheap. Look at Plug Power and ITM, and they're all going to electrolyze. It's going to be free.
It's when you look at the simple thermodynamics of converting renewable electricity to hydrogen and running it in a fuel cell vehicle, you end up with about a quarter, or slightly less than a quarter of the energy you started with the renewable electricity. You go through electrolysis, compression, transportation, fuel cell, drivetrain. You end up with about a quarter of the energy you started with. If you do that for an electric vehicle, you end up with about 70%, and the ratio of those two is near enough a factor of 3.
The way I put it is, it doesn't matter how cheap your cake is, the ingredients are always cheaper.
Exactly right. The ingredients for electricity.
And also, you haven't touched on maintenance costs. I suspect that's something else that you're gathering data on.
I think maintenance costs are a big issue. I mean, this fuel cell vehicle is way more complicated, more issues, moving parts, expensive platinum catalyst, all that stuff is much more expensive. So the real question, Michael, is can you do the logistics with a battery electric vehicle?
Logistics? Do you mean the loading and unloading, or do you mean the charging and the fueling?
The charging and the distance you need to travel without time penalty, and that's the critical thing, right? Logistics is a highly time dependent thing. You can't add time penalties, significant time penalties for charging of vehicles. And so the question is, can you do UK current logistics without time penalties with electric vehicle? And the answer to that is we've been researching that for a couple of years and have concluded that it is perfectly possible to do currently UK logistics using battery electric vehicles by charging at rest stops and by charging at warehouses when vehicles turning around for typically 20 minutes or half an hour, by fast charging at on these locations, and even using overhead power lines, which is another story. You can do logistics with electric vehicles.
Presumably the starting point, which you didn't mention, is that these trucks are parked somewhere at night or for some period of each day, and you start with slow charging there, and then you're doing top-ups along the way. Is that, I don't want to put words in your mouth, but
yeah, well, not all vehicles do that, and some vehicles run 24/7 with alternating drivers, and you have to be able to deal with those as well. So we do need to have enough time during the day to charge vehicles, but we think that it is possible to run a logistics system on electric vehicles only. And given that, there's no incentive to buy buy hydrogen-powered vehicles, which have much higher capital costs and much higher running costs.
Right.
And yeah.
But doesn't that put an enormous onus on these rapid charging? I mean, we're talking about vehicles that will charge at what, half a megawatt, maybe a megawatt, and then you might have 20 of them all in a truck park outside, I don't know, Dover, or outside the logistics triangle in the center of the country, or over at Felixstowe. How on earth are you going to get? I mean, isn't that just an enormous pulse that goes onto the grid, because you've got these 20 trucks arrive and they all got to charge at the same time? How do you get around that?
Well, it's pretty well continuous, but if you wanted to refuel those trucks with hydrogen, you would need 3 times that amount of electricity.
That's if the hydrogen is locally generated.
That's if the hydrogen is locally generated. Well, so hydrogen distribution is one of the things which is not talked about. But there's an interesting little statistic. If you take a diesel fuel tanker and you want to replace it with a bunch of hydrogen tube trailers operating at 700 bar, compressed hydrogen at 700 bar, Do you know how many of those tube trailers it takes?
I shudder to think. You're about to tell us, though.
I'm about to tell you. It's 18. So you need to replace every fuel tanker with 18 hydrogen tankers.
And that's because hydrogen, although there's lots of energy per kilo, but there's lots of cubic meters per kilo as well.
And 700 bar, you've got thick steel pressure vessels to hold it, and they're quite heavy. So so getting that hydrogen around the country by tube trailer is non-trivial. And then so you say, all right, well, let's do it by pipeline. To which I would say, well, how many of the existing refueling stations are connected by gas pipelines, even if you were able to use them?
Yeah.
And so then you end up with electrolyzing at the refueling station. And if you're going to do that, you need 3 times the amount of electricity.
It's also being promoted as a great solution because the grid is constrained. There's all sorts of local DNO areas, distribution network areas on the electrical grid that haven't got the capacity. And of course, if you say, well, we'll bring in hydrogen, well, that's hard, and then we'll make it locally, but that doesn't solve your problem, makes it worse.
Makes it worse.
Just if we've got time, I would love to have you talk about the catenaries, because that's where you and I first met. That I got hold of, and somebody sent me a draft of a paper you wrote about catenary. So this is charging on some of the major motorways of the UK, and it seems very sort of Heath Robinson and ridiculous and absurd that we're going to have. They're going to look like tramways, but your calculations are that it makes a whole hell of a lot of economic sense. Talk us briefly through that, and then I'll let you go.
Indeed, thanks, Michael. Well, so the first thing is, of course, electricity much prefers to be transported in wires than in boxes. So it's much more effective to move it to the vehicle than have the vehicle carry it. The basic kind of technology that we're talking about is the sort of system that is used to power trams and trolley buses in cities, and is well proven. In fact, it's been well proven in a bunch of trials in Germany running on the motorway as being safe and effective for trucking as well. The big advantages of it are, first of all, that, of course, it's the most efficient way that you can power a vehicle because you don't even have to take electricity in and out of a battery. It comes straight from the grid, straight from the wind turbine, transmitted straight to the vehicle, into the inverter, and into the motor. That's the most efficient way that you can run a vehicle. Nearly 80% of the electricity ends up at the wheels, which is fabulous. So the carbon emissions are the smallest. The battery sizes are the smallest, and that's highly beneficial because of constraints on the battery supply chain and so on. And the carbon emissions are lowest, and the effect on the trucking is the least because you have the smallest possible battery. So that means that if you're running heavy loads, for example, you're carrying steel or something like that, which would otherwise be constrained by the weight of the battery, so you wouldn't be able to carry as much stuff as you want because of the battery, you don't have that constraint because you've got small batteries. You have small batteries to take the vehicle from the motorway to the warehouse, 10, 15 kilometers away. So it drops its pantograph and runs on battery power to its destination, runs back and charges while on the motorway. So all of those things are a big benefit. The total cost of installing such a system on the UK's motorways would be about £20 billion. Well, actually, our recent little hiatus in government cost us more than £20 billion. That's quite clear. So if they did, instead of having that hiatus, they just put it into the transport industry, we could have decarbonised all the trucks much more effectively. £20 billion sounds like a huge amount of money, but you can compare it with £28 billion, which is the Department of Transport's budget for roads for the period 2020 to 2025. So we're spending about 50% more than that, than the 20 billion. in the current budget for roads. So it's right within the realms of a practical project. But the big advantage is that it can be done quite quickly. It is the lowest carbon, lowest cost, most efficient system for the country.
And presumably we're not talking about every road. I mean, 20 billion doesn't sound like a lot. And I know that when I first saw your paper, I said that just double it, just without, I hadn't even read the paper. And I said, it seems too low, just double it. But you're really only talking about a small number of motorways that, because it is for those longer distance trucks, which are not on every road, are they?
That's absolutely right. So they do spend some time, some of those trucks do spend the time tramping around the wilds of Scotland and Norfolk and so on. And you do need to have some static charges and larger batteries on a small proportion of vehicles that do those kinds of journeys. But the majority of vehicles which just run up and down the motorway, warehouse to warehouse, can be powered entirely by such a system. When you stand next to the system in Germany and you see it, it just works. And you think, well, that's obvious. Of course that works. It's brilliant.
And presumably the 20 billion, or if I'm right, 40 billion, which is, by the way, I also think is a relatively small amount of money, but, maybe my perspective is distorted by, what we spent during the pandemic and various crashes.
They're paying you too much at Bloomberg, Michael.
Yeah, maybe I'm just exactly earning too much. No, but presumably the trucks pay for themselves because they then become cheaper. So you don't need to worry about that. That number is only the infrastructure, but actually you don't need to then start adding, well, you've got some equipment on each truck, but that'll be less than a hydrogen fuel cell or a much bigger battery that would otherwise be needed.
That's exactly right. It's the cheapest thing you can do to the truck, right? You take this battery electric platform with a small battery and you put a 10,000 pound pantograph on the roof. And that's really a low cost compared to all the other things you can do. That's a very low cost addition. Yeah.
And you're charging, it's not just, you said that the electricity can go straight into the motor, but you are also charging as you go. It's not all going into the motors, it's also going into that smaller battery, presumably.
Yes, and that's important because it means that you don't have to charge at the warehouse. It means you don't have to have a big grid connection at the warehouse, which is expensive and time consuming and complicated. And it also means you don't have to stop at the warehouse. There are plenty of operations where the tractor unit drops its trailer at the warehouse and goes off again. It doesn't have half an hour to stop and charge. And it can just charge on the motorway. So it means that the vehicles never have to stop. They can keep running without having to stop to charge.
Systems thinking, right? Cheaper trucks, more expensive road maintenance and road infrastructure, but not having to do building out all of this hydrogen fueling stations, hydrogen pipelines, and some way of making hydrogen, which is inevitably going to be more expensive because you can't make you can't make a cake cheaper than its ingredients. So fabulous stuff. Unfortunately, David, we are. I'll let you go because you're the one that's time constrained. So go ahead.
Let me just say one final thing. Because of the energy efficiency of this approach, it saves a lot of money, and it's financially viable, financially the most attractive for the vehicle owner, but it can also, the infrastructure can be paid for by private finance. So although it's cost 20 billion to build the infrastructure, it can be privately financed. And so that just needs, those sort of government.
That would be presumably your calculations. That presumably works because on a total cost of ownership, total cost of operations basis, it will be cheaper than diesel. And therefore there ought to be a financial bit of wizardry that my mates in the City of London could do that should not even hit the Treasury's budget. Is that right?
Well, actually, what it means, because of that energy efficiency, is that Treasury can raise revenue through electricity sales to account for some of the diesel tax that that they won't be getting. So rather than subsidizing hydrogen, they can be generating revenue from electricity sales on the same vehicles, and everybody comes out a winner.
Fabulous. You could say, well, what's not to like? But of course, we are not gas network operators or gas extraction distribution companies, because I'm sure that if they were on this call, then they would find plenty of things not to like about it. I'm going to let you go. I would have loved for you to talk about direct air capture and how many Rolls-Royce Trent engines it would take to actually remove some carbon from the atmosphere. I think we're going to have to leave that perhaps if I have you back for a later episode. David, it's a huge pleasure, as always, to talk to you and to have you. I'm thrilled that you came on Cleaning Up here today.
Thanks, Michael. It's been a pleasure.
So that was David Cebon, Professor of Engineering at Cambridge and expert on all things transportation and net zero. My guest next week will be Meredith Adler. She's Executive Director of Student Energy and an expert in getting young people engaged in climate action. Please join me at this time next week for a conversation with Meredith Adler. Cleaning Up is brought to you by Capricorn Investment Group, the Liebreich Foundation, and the Gilardini Foundation.